Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we're continuing a look at derivatives of carboxylic acids. We're looking at the most reactive of the carboxylic acid derivatives, the acid chloride. We're going to begin by examining the nomenclature of these derivatives. Now, the nomenclature of acid chlorides is based on the parent carboxylic acid. So whenever you have an acid chloride, such as this molecule, the first thing you should do when you see an acid chloride is imagine the chloride is an OH and name it as if it was a carboxylic acid. If I have this carboxylic acid, the IUPAC name is ethanoic acid. Do you recall the common name? The common name is acetic acid. Now, when you have the acid chloride, it's derived from this name. In order to name the acid chloride, you take the ic acid and replace it with YL and add chloride. The same applies to the common name. The ic acid is replaced with YL. Chloride. Chloride is a separate word. So, in order to either provide IUPAC or common name, name the parent carboxylic acid and then drop ic acid and replace it with YL chloride. Okay, how do we prepare acid chlorides? Preparation. Well, acid chlorides are prepared by using reactive reagents such as thionyl chloride, thionyl chloride is SOCl2, or reagents such as phosphorus trichloride. PCl3. If you take a carboxylic acid and react it with these reagents, if you take it with SOCl2 and ether, the reaction is very reminiscent of what we saw with SOCl2 and ether in alcohols. The OH is replaced with the chlorine. And SO2 gas is produced, which bubbles out of the ether solution, as well as HCl gas. which also bubbles out of solution. The arrow up, remember, means bubbling out of solution. PCl3 in ether also makes the phosphorus trichloride, also makes the acid chloride. But in this case, phosphorus acid is formed. Okay. And that represents it for the preparation of acid chlorides. Now, we're not talking about acid bromides because, as indicated previously, acid bromides are more reactive. Typically, they're not stored in a bottle, but used as soon as they're prepared. Acid chlorides can be stored in a bottle and used as one sees fit. Acid bromides are far more reactive than acid chlorides. Well, let's take a look at the reactions. Of acid chlorides. Now, as stated, acid chlorides represent the most reactive of the carboxylic acid derivatives. Chloride and bromide are the weakest bases and hence the best leaving groups. The mechanism of reactivity of acid chlorides is a two-step process referred to as nucleophilic acyl substitution. So, if I was to write down the mechanism, the name of the mechanism is nucleophilic acyl substitution. So nucleophilic acyl substitution. The first step involves nucleophilic attack of the acid chloride. So step 1 is nucleophilic attack. So we have an acid chloride. We react it with some nucleophile, presumably as a lone pair. It goes for the delta plus on the carbon. Pi electrons move out. We get a short-lived intermediate, which looks like an alkoxide. But because we have the good and leaving group chloride, a second step happens very quickly. And that is elimination of chloride. So elimination of chloride. The O- group that is formed. The lone pair of electrons on oxygen dump back in to reform the pi bond. The chloride is kicked out, taking its 2 electrons. And you now lose chloride, minus Cl minus. And you get RC double bond O and U. And therefore, the nucleophile has substituted for the chloride. This represents the primary reaction path of all acid chlorides, nucleophilic acyl substitution. Let's look at some of these reactions more specifically now. And let's begin by reaction with water. Remember that all carboxylic acid derivatives are called carboxylic acid derivatives because when they react with water, they produce carboxylic acid. Water reactions are referred to as hydrolysis reactions. Water reacts with acid chlorides to yield carboxylic acid. If we react it with HOH, it's 2 lone pairs on the oxygen, water can come in, attack. If it does so, we produce the intermediate that we had previously. But this time the nucleophile, of course, is H2O. Once it's bound, it becomes positively charged. The electrons dump back in to make the pi bond. We lose the chloride. We have the protonated carboxylic acid, which very quickly can lose a proton, minus H plus, gives me RC double bond O, OH. Now, very similar to the hydrolysis reaction is the alcoholysis reaction, where we replace water with an alcohol group. If we repeat this reaction, but say we use methanol, we can envisage forming the exact same species, except instead of being OH2 plus, we now have this OCH3 with an H off of it, lone pair plus. And if we now go minus Cl minus, you see we can form OCH3. H positive. Now, in the case of alcohol, as well as water, if desired, you can use a base to help with this deprotonation step. Now, you have to remember, if you had used it in the case of water, you would probably deprotonate the carboxylic acid as well. And this would make a carboxylate salt. And so we typically don't use it in the case of hydrolysis. But since we're forming an ester here, once the proton's pulled off the ester, that's all that happens. So often we throw in a base to facilitate this process, and the base that is often used is pyridine. Pyridine is a poor nucleophile, and it can come in with its lone pair and grab the proton and form the pyridinium cation. Once that's done, you will have finished and produced your ester. The nice thing about pyridine, because its lone pair is sp squared, it's not very nucleophilic, but it certainly is sufficiently basic to remove a proton off an ester. So the overall reaction is methanol with pyridine. Okay. So if you take methanol with pyridine, you can undergo nucleophilic acyl substitution and generate an ester. So, reaction or hydrolysis with water produces carboxylic acid. Reaction with alcohol or alcoholysis, reaction with methanol and pyridine will produce ester. We can continue with a variety of different nucleophiles. For example, we can look at reactions with ammonia or primary and secondary amines. If we react with these molecules, the nice thing about this is that the base can serve as both nucleophile, the amine can serve as both nucleophile, and it can also act as base. So you don't have to throw something like pyridine in. For example, suppose we're doing a reaction with methylamine. And suppose we let the reaction go, so we get the same attack. Notice that the first step is always the same. Nucleophilic acyl attack, forming the O-. In this case, we get an NCH3. We've got an H and an H positive. Cl, O-. And then we kick out the chloride. It is the same reaction picture over and over again, just with a different nucleophile attached. Now we have NHCH3. We have an H attached, giving us a plus. And we lost Cl. What's nice about this is if you use two equivalents of amine, one of them can act as base. So if you like, one of the CH3NH2s comes in and goes off as CH3NH3 plus. And that generates your amide, or in this case, N-methyl ethanamide. We'll be learning the proper nomenclature, or how to name amides, ethanamides, sorry, when we get to amide chemistry. Along with this is we get the methyl ammonium chloride. So overall, this reaction proceeded by using two equivalents of CH3NH2, one that acts as nucleophile and one that acts as a base. Reaction with carboxylate salts can facilitate the formation of anhydrides. If I take an acid chloride with a deprotonated carboxylic acid or carboxylate salt, we can react. The carboxylate will certainly attack the carbonyl, giving us our intermediate. And of course, we can reform the carbonyl, kicking out chloride, so -Cl-, and we end up with an anhydride. Now you might say, well, we learned how to make anhydrides earlier by reacting at high temperature and eliminating water. Note that anhydrides react with water to give back carboxylic acid, so that's an equilibrium. What's nice about this reaction is it will go to completion in high yields and give you better yields and better formation of the final product. It can also produce asymmetric anhydrides, which can be useful if the R group is different than the alkyl group used in the carboxylate. Now, one reaction that we have covered, of course, with acid chlorides previously is the reaction with aromatic hydrocarbons, or what is known as Friedel-Crafts. Friedel-Crafts acylation. Friedel-Crafts acylation involves the formation of what is called a resonance-stabilized acylium ion. The acid chloride is reacted with AlCl3. The AlCl3 is a Lewis acid with an empty orbital and forms AlCl4-. It abstracts the chloride. This produces a positive charge on carbon. This is resonance stabilized and this whole thing represents a resonance stabilized acylium ion. Now, the resonance to stabilize the psyllium ion is a powerful electrophile. And so if you attack a benzene, the pi electrons from the benzene will go for the carbon, and you will produce a C double bond O, CH3, H. You'll produce a resonance stabilized benzenonium ion, where we can move the positive charge around the ring. Now the resonance stabilized benzenonium ion, the whole thing, reacts with AlCl4-. The AlCl4- abstracts the hydrogen, I'll circle this hydrogen, and produces HCl and ACl3. So AlCl3 is your catalyst. And you're finished left with the ketone, in this case acetophenone. So Friedel-Crafts acylation was a methodology of substituting an aromatic ring and producing a ketone. Subsequently, the ketone could be reduced via the Clemmensen reduction, and the Friedel-Crafts acylation methodology was a way of making alkyl benzenes that had not undergone a 1,2 shift. That is, you could get propylbenzenes rather than isopropylbenzenes from this methodology. Very important as a reaction was the reaction of acid chlorides. Let's use benzoyl chloride this time, with Grignard reagents. So we're going to react this with a Grignard reagent. We're going to hit it with a molecule like methyl magnesium bromide. If we did that, remember magnesium's more electropositive, carbon's more electronegative than magnesium, so it's like a source of C-. The methyl minus can attack the carbonyl, producing the alkoxide anion. The short-lived intermediate quickly gives way to subsequent reformation of the carbonyl bond and the departing of the chloride. It's a good leaving group, -Cl-. And so what we end up with, once again, is our acetophenone molecule. But the Grignard's so reactive you can't stop here. Another molecule of methyl magnesium bromide will attack. And it'll go for the ketone. And you will produce the alkoxide salt with 2 methyls now off of the carbon. What happens next? Usually destroy Grignard reagents by adding 2 H3O+. If you throw in H3O+ in a separate step, you will protonate and generate the alcohol. So with Grignard reagents, you alkylate or reduce the acid chloride right through to an alcohol. So reaction with Grignard leads to complete reduction, complete alkylation. This also applies if you use methyl lithium. But what if you want to stop at the ketone? How do you prevent further alkylation? Well, this requires the use of a special reagent, a cadmium reagent. Cadmium reagents are milder alkylating reagent than Grignards. You can prepare them by taking cadmium dichloride and reacting them with 2 equivalents of the Grignard. So you could use methyl magnesium bromide, and you would make dimethyl cadmium. Now, this type of reaction only works for methyls, primaries, or phenyl alkyl groups. So, the only type of Grignards you can use are methyls, primaries, or phenols. If you do that, and instead of the Grignard you use dimethyl cadmium, well, this reaction if you use dimethyl cadmium, would stop at the ketone. So, if you don't want the alcohol, and you want to stop at the ketone, use a cadmium reagent. However, one could raise the question, how do you put on a secondary group, alkyl group? How do you make a ketone with a secondary alkyl group off of it if cadmium reagents only work with methyls and primaries? In order to do this, we have to use a dialkyl copper reagent. Dialkyl coppers can be prepared utilizing alkyl lithiums. So if you had 2 isopropyl lithiums and you reacted them with cuprous iodide, you could prepare diisopropyl cuprate, a lithium diisopropyl cuprate. Lithium diisopropyl cuprate is more powerful an alkylating agent than DialkylCadmium, but it's a milder alkylating reagent than lithium reagents or Grignards. If I take a molecule like benzoyl chloride and I react it with lithium diisopropyl-cuprate. I do the reaction in ether, and I'm careful to keep the reaction, because it's a little stronger than alkyl-cadmium, between 0 degrees Celsius to minus 78 degrees Celsius. I can put the secondary alkyl group in place of the chloride and stop at the ketone. And so I can make phenyl isopropyl ketone. All right. So, alkylating with Grignard alkylithium is hard to control. You can't stop at the ketone and you put 2 alkyl groups on. DialkylCadmiums are good for methyl primary phenyl groups, but when you have to put a secondary group on, you use a dialkyl copper. What about reducing to hydrogen? What if instead of putting an alkyl group on, we want to put a hydrogen on? We want to make an aldehyde. Well, reduction with lithium aluminumhydride leads to the formation of alcohol. Lithium aluminumhydride is a very powerful reducing agent, and you can't stop at the aldehyde. Indeed, placing 1H- on will go through the alkoxide, you'll reform, and you'll get the aldehyde. But then the aldehyde subsequently it gets attacked and an H- gets placed on, and you end up putting 2 H's on the carbon, and then the oxygen gets protonated and you make the alcohol. If you want to stop the reaction at the aldehyde, we have to reduce the reactivity of lithium aluminum hydride. The only way to do that is to take 3 tert-butyl alcohols. If you take 3 tert-butyl alcohols and react it with lithium aluminum hydride, remember, aluminum is less electronegative than hydrogen. So the aluminum hydride is a source of H-. The OH group, oxygen is more electronegative, so the OH provides H+. The H- will react with the H+ to make H2 gas, and oxygen will bind to the aluminum. What happens then? Well, what happens is you get this aluminum with 3 oxygens attached to it that are tert-butoxides. Now, essentially, we replace 3 H- with these bulky tert-butoxides. This whole unit is negatively charged, and so there's an associated lithium. If you like, we can name this as lithium tri-tert-butoxy aluminum hydride. So 2 words. Lithium's 1 word and the tritert-butoxyaluminumhydride is another. Now this molecule is a much milder reducing agent. It is a milder source of H-, unlike lithium aluminum hydride, which can deliver 4 H-, this can only deliver 1 H-, and its reactivity is reduced because of the bulky tert-butyl groups. There's a steric effect reducing the interaction. If I repeat the reaction of the ethanol chloride, but this time I use lithium and I use HAl OC CH3 3 times, squiggle bracket 3 times. If I use the lithium tritert-butoxyaluminumhydride in a step 1, and then I follow that with a step 2, such as H2O or H3O+, then what will happen is I will stop at the aldehyde. Okay. So we can reduce acid chlorides right through to the alcohol, or by using less reactive reducing agents such as lithium tritert-butoxyaluminumhydride, we can take it to the aldehyde. Now the next reaction we want to look at is a little different from all of the reactions. Every reaction we've looked at has involved some kind of nucleophilic attack at the carbonyl. But the next reaction we want to look at is an alpha-halogenation reaction. And the alpha-halogenation reaction that we're going to examine here really was a solution to a major problem. You see, alpha-halogenation can only work if you can have appreciable amounts of enol in solution. Now it turns out that acid chlorides have appreciable amounts of enol in solution even though they're small. Yes, the equilibrium shifted to this left, but there are tiny amounts of the enol present. Now the enol is important to alpha-halogenation because it is the enol that drives the reaction. That is, if I throw in some halogen, is the pi bond of the enol that attacks the Cl2, causing the CCl bond to rupture. And once that happens, you lose HCl, and you will alpha-halogenate. You will get RCH, Cl, C double bond O, Cl. Now here's the deal. This is a problem for carboxylic acids because the concentration of enol when you have carboxylic acid is extremely low. If I compare the carboxylic acid enol concentration, guess it's actually an enediol. This concentration is much lower than the concentration of enol in the above reaction. Because of this, and its extremely low reaction, if I throw Cl2 in, the concentration is so small, the reaction so slow, it effectively does not occur. And so the dilemma that resulted was, how could we make a carboxylic acid that was alpha-halogenated, knowing that we could do it for the acid chloride? Well, the answer lay in the fact that acid chloride that had been alpha-halogenated could be reacted with carboxylic acid. And the acid chloride would react in such a way as to chlorinate the carboxylic acid. In other words, you get RCH2, C double bond O, Cl. The chlorine goes there, and what was the acid chloride becomes a carboxylic acid. In other words, if we keep it simple, think of it as the chloride exchanging positions with the OH. Now, we can use or prepare acid chloride from the carboxylic acid using PCl3. So if I had taken my carboxylic acid, hit it with PCl3, this carboxylic acid right here would have become acid chloride. The acid chloride has appreciable enol concentration, so if you throw in Cl2, you get alpha-halogenation. But carboxylic acid can also react with the acid chloride to make the carboxylic acid. So if we alpha-halogenated the acid chloride, then it could be converted back to alpha-halogenated carboxylic acid, the molecule we really want. Well, this reaction and the reaction with PCl3 plus Cl2 to form this really gave the solution for making this guy. How? Well, suppose we start with our carboxylic acid. We can't throw Cl2 at this because it won't alpha-halogenate. If we throw a lot of PCl3, it all converts to acid chloride. And yes, we could convert it back afterwards. It'd be nice if in one step you didn't have to react, make the acid chloride, then hydrolyze it and convert back. What if you used a tiny amount of PCl3? What would happen? Let's use cat in brackets to indicate a catalytic amount of PCl3. What would happen if I used a tiny amount or catalytic amount of PCl3? Most of the material would remain as carboxylic acid. But there'd be a tiny amount of RCH2 C double bond O Cl. Now suppose with the catalytic amount of PCl3 you had thrown in Cl2. The Cl2 does nothing to the carboxylic acid, but the tiny amount of acid chloride would react with the Cl2, making the alpha-chlorinated acid chloride. But we learned that this catalytic amount of acid chloride, once it's alpha-halogenate, can react with the carboxylic acid. And if it does, this guy becomes RCHCl C double bond OH, plus you get more acid chloride. And the cycle can continue as long as you've got some carboxylic acid present. Eventually you're going to run out of carboxylic acid, and so what you're going to end up with when you're completely done the reaction is a lot of RCH, Cl, C double bond O, OH, and only a tiny amount of RCH, Cl, C double bond O, Cl. And in fact, if you destroy the catalyst and extract from water, even this will convert back to carboxylic acid. So you could do a one-step reaction with a catalytic amount of PCl3. The carboxylic acid did not get alpha-chlorinated. The catalytic amount of PCl3 formed a catalytic amount. I'm going to put this as a cap. A catalytic amount of the acid chloride. The acid chloride got alpha-halogenated, and then it reacted with the carboxylic acid. Okay? When it did, it became carboxylic acid, and then this carboxylic acid converted to acid chloride, and the cycle continues. Once the carboxylic acid ran out, you were left with a catalytic amount of acid chloride, and most of it alpha-halogenated carboxylic acid. But it's important to remember that this alpha-chlorination occurred only via the acid chloride, not the carboxylic acid. This reaction is developed by three chemists. It's called the Hell-Vollhard-Zelinsky reaction. For alpha-halogenation of carboxylic acids. By utilizing the acid chloride's reactivity, it was possible to make alpha-chlorinated carboxylic acid in a single step. Otherwise, you would be forced to convert it to completely to acid chloride, alpha-chlorinate, and then convert it back. Okay. Well, that's it for acid chloride chemistry. Next lecture, we're going to look at the next carboxylic acid derivative and hydrides. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.